All right, let's take a look at question 1. So in question 1, we are given figure 2. Okay, so in this figure, right, this figure 2 shows the flood prevention system at the Marina Barrage, where water is being pumped out from the Marina Reservoir to the sea in instances of heavy rain. So the water is being raised, okay, the water is raised from the reservoir to the sea. Okay, the height difference of the reservoir and the sea is 1.2 meter, and 200 meter cube of water is released per second to maintain the reservoir's height. Calculate the power required by the pump if it's 80% efficient. So what we know is they take water, 1.2 meters, they take water and pump it out, right? And in order to pump it out to maintain the sea level, this water from the reservoir need to be pumped up by a height of 1.2 meters. Okay, so what the pump is doing is it's going to supply the water in the reservoir with gravitational potential energy to lift it up by 1.2 meters, right? Okay, so that it is pumped out at this point here. Okay, so to find the change or the gain in gravitational potential energy of water, we'll use the formula mgh, right? mgh. Okay, so we know that h is 1.2 meters because that's a gain in height of 1.2 meters. Okay, g is 10 meter per second square. Okay, and what is m? What's the mass of water that's being lifted? We are given 200 meter cube. Okay, 200 meter cube is not mass, it is volume. Here they give us density. So why do they give us density and volume? Because density is equals to mass over volume. So to find mass, we will take density times volume. So in other words, to find this mass of water that is being lifted, we are going to take the 200 meter cube times 1000 kg per meter cube to find what is its mass. Okay. Okay, then we know what is the amount of useful energy that is being supplied by the pump to pump the water up 1.2 meters. Okay, so in 1 second, we know that the mass of water released is 200 meter cube times 1000 kg per meter cube, which gives us 200,000 kg. Okay, so we found the mass of water being released. Okay, next we are going to find the gain in gravitational potential energy, which is equals to mgh. M is 200,000 kg, g is 10, and h is 1.2. So this gives us 2,004 or 2,400,000 joules. Okay, and this occurs in 1 second because it's per second here, right? Per second means 1 second. So you divide by 1 second, it tells you the power. So you get 2.4 million watts, which is the same as 2.4 megawatts, because mega means 10 to the power of 6. Okay, now we know that the pump is not 100% efficient, it's only 80% efficient, right? So if it is only 80% efficient, this means that 80%, okay, produces 2.4 megawatts, which is used to lift the water. Okay, the rest is being lost. Okay, so how do we know how much power did the pump supply? So, well, to find the power input, we will take useful power divided by efficiency. So we'll take 2.4 divided by 80% to find what is the power required by the pump. So the answer for part A is 3.0 megawatts. Of course, you can also leave it in watts, so it'll be 3 million watts. Okay. Moving on to part B. So in part B, you're asked explain why there's a need for a higher power input than the answer in A in real life. So think about it. If you want to pump water from the reservoir to the sea, okay, can you put your pipe here? No, right? Probably you have some seawater backflow back to the reservoir. Okay. So in order to do so, you probably need a pipe that is higher than the sea level. You pipe the water slightly higher than the sea level, right? So that you know that it will go in, and the seawater will not be able to touch the pipe and backflow back to the reservoir. So in other words, right, the water needs to be discharged at a higher level than the sea level to prevent backflow of the water from the sea back into the reservoir. So if you want to discharge it at more than 1.2 meters, means that you'll need more energy, right? So this means that the water needs to be raised more than 1.2 meter high, resulting in more gravitational potential energy that needs to be supplied to the water. So in other words, right, the pump should supply water slightly higher, right? so that the seawater won't get in and flow back. Okay, so I need to pump from here all the way to here. Okay, there is, so because I'm going to pump it out from here slightly above, instead of 1.2 meters, it is more than 1.2 meters above the reservoir, right? So it needs to supply more gravitational potential energy. Okay, so that is the answer for part B.